So my talk is going to be about a theorem, and I'll explain what the theorem states and how it's different from other theorems, especially the one being presented 2 months later. And then I'll give as much proof as fits into 15 minutes. So the theorem is the following. We were given, it states about the fact that the Fisher-Hall metric is unique under certain invariants. And the precise variance assumptions are as follows. We take a compact manifold with a boundary of dimension at least 2 or higher, and it considers the space of all probability densities on this manifold. And probability densities in this case are all smooth probability densities that are n over 0. And smooths are actually infinitely often immeasurable, so really probably smooth. And if you're given on this space of smooth non-vanishing probability densities remaining a metric, which is invariant under the action of the diffeomorphism group, and again, smooth diffeomorphism group, then this remaining metric already has to be a multiple of the Fisher-Hall. Okay, now a couple of comments. So how does it differ from other theorems? So first of all, it differs mostly in the assumptions. The conclusion is the same. The Fisher-Hall metric is unique. It's unique under what assumptions? All we assume here is that it's defined on the space of smooth non-vanishing probability densities. So for, I guess from a statistical point of view, it's a very small space. It doesn't contain delta distributions. It doesn't contain piecewise constant probability densities. They have to be actually smooth. And regarding the invariance, it's invariant under, again, similar small group. It's invariant under smooth diffeomorphisms. Not sufficient statistics, not measure-preserving maps, not measurable maps, but simply smooth maps with smooth inverses. And under these conditions, we have this statement. Now, why do we want to have this formulation? Well, because the setting of smooth maps, smooth densities, smooth diffeomorphisms is a nice natural setting to do infinite dimensional differential geometry. Under this condition, the diffeomorphism group of M is an infinite dimensional Lie group modeled on a Frege space. Similarly, the space of probability densities is an infinite dimensional manifold. So we can do proper infinite dimensional geometry. So, a couple of notations. M is a compact manifold without boundary. Dimension is little m. Diff of M denotes the group of all smooth diffeomorphisms of M. And for this talk, we assume M is orientable. We can do this in another orientable case, but that's for a different time. Dense plus are the positive probability densities. Because M is orientable, these are simply the M forms, number vanishing M forms. And they restrict ourselves to probability densities are those M forms which are integral equal to 1. Now, the first space is an open subset of a vector space, so the tangent spaces of that space are simply the M forms. The tangent spaces of probability densities, this is an open subset of an affine space, are all M forms which have integral equal to 0. And we'll need one subgroup of the diffeomorphism group, which are those diffeomorphisms which preserve a given density under the pullback operation. Sort of the volume preserving diffeomorphisms, but we have to make sure we specify what volume it is that we are preserving. Okay, this is what we actually prove. This is a theorem we prove, and then a statement about the uniqueness of the Fisher-Hall metric sort of comes out as a corollary. The statement is that if you're given a smooth bilinear form on the space of all densities, which is invariant under the diffeomorphism group, then it really can contain exactly, can consist of only 2 pieces. One is the Fisher-Hall metric, and the second one is simply the bilinear form obtained by integrating alpha and integrating beta. And we can combine those, and because it's invariance under diffeomorphisms always preserves the volume, they can be combined using functions that can depend on the total volume of the space. Now, if we restrict ourselves to the corollary, if you're given a metric on the space of probability densities, well, we extend it equivariantly to the space of all densities. We have this classification result. This has to vanish because tangent vectors to probability densities have integral equal 0, so it has to be this thing. Okay. One more thing, the assumption here is a little bit weaker. We don't need symmetry. We don't need positive semi-determinants. Simply a smooth bilinear form which is invariant, has to be symmetric, has to be positive semi-determinant. Okay. That's the statement of the theorem, and this is the theorem we want to prove. I will make a couple of comments why dimension bigger or equal to 2 is necessary in the next step. Okay, so proof goes in a couple of steps, and we'll do some of them, and I'll First of all, we use the invariance under diffeomorphisms to reduce the problem to only have to consider its behavior at one probability density. So we assume G is one of those invariant smooth bilinear forms, and we fix some probability density mu 0. And then Moser's trick tells us that any other density can be pulled back by some diffeomorphism. There exists a diffeomorphism which pulls back this diffeomorphism, which pulls back this density to a multiple of mu 0. And the multiple is determined by the total volume. And then by the invariance, we look at G mu, because it's invariant as a diffeomorphism, it has to equal this. So it is given by how the bilinear form behaves on mu 0 and so on. So if we know that at mu 0, or at multiples of mu 0, our bilinear form has this form, we're done. Now, we've used some of our invariants to reduce the problem. The question is, what invariants do we have left to make any statement about G at mu 0? Well, we have left the invariance of G under the volume-preserving diffeomorphism group. And in dimension 2 and higher, this is enough invariance, this group is big enough that we can still make statements about our bilinear form G. Now, if we have one dimension, if we have a one-dimensional compact manifold, essentially we have a circle, that only volume-preserving diffeomorphisms are simply the rigid rotations. So the left is only a one-dimensional invariant, one-dimensional symmetry group, and this doesn't allow us to say it. In fact, in one dimension, there are many invariant Riemannian metrics on the basis of probability densities. But in dimension 2 and higher, we can do it. Second of all, what we do is we restate the problem in terms of distributions. So instead of working with M forms, we look at a G defined on functions, and we simply map functions to M forms by multiplying with mu 0, and then we have a bilinear form of functions. A bilinear form of functions can be represented as a linear map from functions to distributions, and a linear map from functions to distributions using the Schwarz kernel theorem can be represented as distributions on the product space. And all those three equivalences are sort of given here. So this is a bilinear form. This is a linear map from functions evaluated to distributions, evaluated paired as a function, and this is a distribution on the product space evaluated on a tensor product function. And then we use invariance. Sort of the infinitesimal version of invariance says we use not the volume-preserving diffeomorphism, but we use the divergence-free vector fields, divergence-free Wither spectra given mu 0. And then it sort of follows and in steps like the question is, are these divergence-free vector fields enough to characterize things? And sort of step 1 says, was there enough to characterize constant functions? If the Lie derivative of a function, if all Lie derivatives of a function are 0 on an open connected set U with respect to all divergence-free vector fields, actually a slightly smaller set, then the function already has to be constant. But constant in this case means it has to be a multiple of our density mu 0 in the sense that evaluated with a function, it has to be this integral. And we see that this integral, that's where we sort of want to end up with. We want to show that distributions are equal to mu 0. So its divergence-free vector fields are enough to characterize constant distributions locally. And then in the third step, we move on to our actual form F, where we state that if F, or the linear form G, and now in the shape of G mapping from function to distributions, in a statement that if F is a function, F is constant somewhere on some region, then the corresponding distribution G check of F in that region has to be very simple. So where F is simple, G of F has to be essentially multiple to 0. And again, you use invariance, you use the fact that you have enough divergence-free vector fields, and so on. And so this fact that where F is simple, G has to be simple, leads then to the fact that if F and G are two functions with disjoint support, so where F is interesting, G is simple, and where G is interesting, where F is interesting, G is simple, leads to the fact that with the disjoint support, then G there has to be simply a product of the integrals, because sort of where F is interesting, well, sort of where G is interesting and F is boring, it has to be sort of the integral of G, and then you apply the same argument to the transpose form, and the only thing that can happen is only lose the integral. And this is already one of the elements we have in the Fisher-Rao statement. And when we said functions with disjoint support, so whenever f and g have disjoint support, it has to be this. This means that we have solved the problem of the diagonal on M cross N. And then we subtract this, and we're left with a new distribution, still invariant, which now has support on the diagonal. And for distribution which has support on the diagonal of a product, there are tools from theory of distributions. So it has to have a very special form, essentially a sum of distributions of just on M and some nice partial differential operators. And then again, using invariance, we can sort of step by step reduce our problem and get to the fact that actually these distributions have to be equal to mu0, and these differential operators actually can be only common. And this leads to sort of the end of that. So this was sort of a very quick overview of the theorem, and it's proved in 16 minutes.
That's gorgeous, you know. I was kidding, you know, because I was sure that you will do more than 15 minutes. But you did it. Okay, that's really, okay. Great talk. Okay, so I think that's good because now we have time for questions. So I'm sure.
No, thank you. Yeah, the theorem is beautiful. Initially, Fisher-Rao metric is defined not exactly in this context because you have probabilities on the space X parameterized by a manifold M. So do you have some extension to this situation?
Right. In a way.
Yes, you want to put a restriction of the on the.
Yes, because
yeah.
you impose some relation between X and M, which is not.
Yes, we will see that in the next talk.
In that this framework, this manifold, you assume you have on every parameterization you have a metric, and they are consistent with each other. And in this case, we just simply say we can already work with the space of all sufficiently smooth probability densities. This is already a manifold, and we can already talk about things like metric on this manifold. We don't need this extra parameterization imposed upon us. That's
my question. Can't we start with probabilities on another space, parameterized by a manifold, assuming that invariant by the homomorphism of the parameterized manifold, and we get unicity. I suppose for doing that, you have to formulate something like more functionalities. Okay?
Probably yes. Yeah. Formulate sufficiently functionalities. I see one of the advantages of this framework is that you don't need this additional, in a way, statistical, like this mapping sort of imposes sort of artificial coordinates on the problem, and this formulates intrinsically. So I would say if you impose enough functionality, probably yes. We're quite happy that we don't have to do this actually.
Okay, so another question? We have
Maybe it's more a remark and a follow-up on your question. If you specify a submanifold actually of the densities that you consider, then you have also to restrict the diffeos that respect this manifold. And in that case, you're also decreasing the number of diffeos that act on it, and you can end up with cases where it's not anymore unique. And that's what's happening with the Gaussian if you just take the covariance matrix and the fixed mean. There's not a unique metric which is invariant by the group that leave the manifold invariant.
But that's what we need more than just invariant. Probably you need to formulate something for maps between different manifolds.
Use the microphone.
You need to formulate properties of the metric for maps between different manifolds.
It's sorry. Just to curiosities. First, why do you need in your construction C infinity? And for example, C1 for density and C2 for transformation is not enough. I am saying that because you do a composition and you compute some Jacobian determinant. And second question is why, just a curiosity, why do you call Moser trick the transitivity of the action of this group?
Moser trick is the proof.
Huh?
Okay.
Sorry?
So the first question.
Is the proof.
I know the answer of the first question.
Okay. Right. Okay. So the first question, I wouldn't say need as so much as well, it's more we only need our Riemannian metric or symmetric form to be defined on smooth densities. I mean, if we start with something that's defined on C1 densities, then it's also defined on C infinity densities. And if it's invariant under C1 or C2 diffeomorphism, it's also invariant under C infinity. So in a way, it's not so much need as we can restrict ourselves to this smallest, so an object find under smaller space invariant under less smaller group.
Yes,
and
it's
still
harder.
get uniqueness. Yes. For the second, I don't know.
Okay. So sorry, so there is this now famous theorem by Chentsov and Morozova on uniqueness and existence of a finitely generated Riemannian metric invariant in the category of Markov morphisms, which extends his early results for finite dimensional case. So although it's finitely generated, so I don't know whether it is, I just trying to see which is, so is it related and which is the generalization of so I suspect if you consider infinite dimensional case and finitely generated Riemannian metric, basically it has a sequence of expanding sequences of simplices. So does it include your theorem, or that's vice versa? What I'm trying to say.
I have the feeling that those two might not imply one the other easily. Yeah, I don't think so. I mean,
so general infinite dimensional simplex of all probability measures include those that has densities. Is that correct?
yes, but you start. The assumption is you have a bilinear form which is defined on some space, and in that case, as far as I understand, it's defined on finitely generated probability densities, and in this case, it has to be defined on all smooth ones. So it's a question: where does your bilinear form live in to start with? Does that make a statement? So my intuitive feeling would be that those are sort of parallel, independent of each other.
Okay, I think the smoothness assumption is, yes, it's really important. No, because you can imagine acting on the derivative of density and so on. So you have a larger range of bilinear operator, which you can consider, and so you can look for invariance. Okay, I think that's something we should discuss after. Okay, so if there is no more urgent questions, okay, we will move to the next talk. Thank you very much.